Let's talk about force vectors. A lot of this class is going to revolve around force vectors. So what is a force vector? Well, let's break it into its components. What is a force and what is a vector? So a force is anything that acts as a push or a pull on something. We know from Newton's second law, F equals ma. So there are several different ways forces can be applied. It can be as simple as, I have an object that I'm pulling on. So this would be a point force, a concentrated force where I have attached a rope to a box and I'm pulling on it. This is a point force. That is concentrated in one spot. We've often seen it as physics, represented as weight, right? So when I have a box that's just sitting on the ground, that box has a force because of gravity. F equals ma. M is the mass of the box. Acceleration is acceleration due to gravity. So the weight of an object, that is a force. We often call that a body force. Other forces, you'll see frictional forces and normal forces. So looking at this box again, as the box sits on the floor, why does it not fall through the floor? Well, that's because the ground is exerting a force right back up, keeping the box in place. So we have this normal force acting on the box that prevents it from just falling through the floor into oblivion. Normal force is a distributed force. It's distributed all across the bottom of the box. It's not just concentrated to one point. It's everywhere the box is touching the floor, there is the normal force. Distributed force. So those are basically the kinds of forces you'll see. Some other ones we'll see reaction forces. Much later in the class, we're going to look at reaction forces and internal forces. Friction, that's one that you may have seen in physics also. If I were pulling on this box, you have a friction force going the other way. That would also be a distributed force because it's acting all along the bottom of the box. So those are some examples of the forces that we're going to see. So now what about the vector portion of this? What is a vector? A vector is a quantity that has a magnitude and a direction. So we saw this in Physics 1 when we would talk about displacement, velocity, acceleration. We would say any of those have a magnitude and a direction. So we keep talking about gravity. The gravity as a vector, 9.81 meters per second squared, is acting downwards, right? It's pulling you in towards the Earth. So it has a magnitude. This is the magnitude, the actual numerical value of the acceleration, and then direction, which is generally we represent it as down. You're being pulled down towards the Earth. So when we do this with forces, it works exactly the same way. If you have a man standing here, he is exerting a force on the ground, F equals ma. So this force is a force vector that has magnitude and direction. It is acting downwards because acceleration is pulling him down. So the force vector, this is our vector notation, is usually either a bold F. If you see it typed, you'll see it typed as a bold F. Or when you see it handwritten, we often just draw the letter F with an arrow above it to signify that this is a vector. And if you want just the magnitude, we'll either write just a normal F like this, or sometimes you'll see magnitude described as these two absolute value bars with an F in the middle. So this is the magnitude notation. And these are the vector notation. Now, when we're describing a vector, we don't normally just say down. We don't say, oh yeah, this vector is going, 3 to the northeast. It's not really how we talk about vectors. There are usually 3 main ways we describe vectors. So the 3 ways we talk about vectors, and we write them and describe them, are using the coordinate system. Sometimes this is called polar, the polar way of describing things, the coordinate system. So, for example, when we draw the XY axis and you have something like this, this is when we would use the angle and the magnitude to describe them. So, for example, F is 20 pounds and it acts as, 30 degrees from the x-axis, measured counterclockwise from the x-axis. So this would be one way to describe them. You can provide the magnitude of it and an angle. The second most common way we describe these vectors is through the Cartesian system. So this is breaking them up into their x, y, and z components and then marking them with the Cartesian notation. So the Cartesian notation is this force vector is the magnitude of F in the x direction times I hat. I is the unit x direction vector, plus the magnitude of force in the y direction times j hat. J hat is the unit vector in the y direction, plus f of z k hat, where k is the unit vector in the z direction. So looking at this side graph here, our f of x is going to be the x component of this line. So this is the x component. This is f of x. For the angle here is alpha. Your y component is along the y-axis. Along the y-axis, this f of y with an angle between the line and y as beta. And then your last one is this z-axis. F of z has an angle between the line and f of gamma. So we can convert each of these so that way if we're given f and these angles alpha, beta, and gamma, we can convert them. So cosine of alpha equals f of x over f, which of course you could rewrite as f equals fx cosine alpha if you wanted to. You can convert it either way depending on what you're given. If you're given the components or if you're given the force as a whole and the angles. So your cosines, you can do this for each one of them. Cosine beta is f of y over f, and cosine gamma is fz over f. And those are all of the magnitude. You can also use a form of the Pythagorean theorem to find the magnitude of f overall. So f is the square root of fx squared plus fy squared plus fz squared. So these are just modifications using our right triangle trigonometric theorems that we already know. We're just applying this to vectors in a 3D space. The third way you can describe these is using something called unit vectors. A unit vector is a vector that has a magnitude of 1. So all it does is provide direction. You're going to have to multiply it by a scalar to actually get the full vector value. So our unit vector is the magnitude of, the magnitude of f x over f I hat plus the magnitude of y of f in the y direction over the magnitude of f j hat plus the magnitude of z over f k hat. So this is just converting to a one single unit. So this just converts it to a magnitude of 1 so that we can provide direction. If we wanted the actual value of the vector, we would just multiply everything by f again, and that would be the actual value of the vector. This is really useful for dealing with force and position vectors. So for example, if you're given some vector that's just hanging out in space, and you're given the coordinate points, like this is sitting at 1, 2, 3, and pretend there's a coordinate system here or something. This is sitting at 1, 2, 3, and this point is sitting at like -1, -2, -3. You'll be able to determine a position vector, and that's when these unit vectors can really come in handy. One more important note, a unit vector is also just cosine alpha I hat plus cosine beta j hat plus cosine gamma k hat. So these two unit vectors are interchangeable. If you're given the position just using the angles, you should be able to find the unit vector, and then you can multiply it by the magnitude and get what the actual vector is. It's a little weird, so let's take a look at an example to kind of clear some things up. It makes a lot more sense in practice than it does to just tell you the theory behind it. Okay, let's talk through this example together. We have this position vector that's out in space. It's not focused at the origin, and we're given some coordinates for the A point and the B point. If you can't see it clearly, I'll write it here. Our A point in space is located at x coordinate 1, that's this distance here, 1. The y coordinate is 2, and the z coordinate is 3. And our B has a position of an x coordinate of 3, a y coordinate of 5, and a z coordinate of 9. So we want to take this position vector. This is a force vector of 700 pounds. And we want to put this in Cartesian form. This is where our unit vector would come in handy. So go ahead and try and see if you can figure out how we would use a unit vector to get this into Cartesian form. And if you'll remember, that's our I hat, j hat, k hat form. So go ahead and give that a shot. Pause the video and come back and we'll work it out together. So the first thing we'll want to do is we'll want to find our position vector. So our position vector usually is represented as r. R is going to be the difference in our coordinates. It's going to be vector addition. So in this case, our x components, if we subtract our b points from our a points, 3 minus 1 for our x components, 5 minus 2 for our y components, and 9 minus 3 for our z components. And that's just taking these and subtracting them directly across b minus a. R is just the vectors, the positions b minus a. That's how we get our position vector. So our position vector here is 2, 3, 6. Now we can also find the magnitude of this r vector. R is going to be the square root of 2 squared plus 3 squared plus 6 squared, which gives us a magnitude of 7 when we punch that in the calculator. So now that we know the r vector and the r magnitude, we can find the unit vector, because our definition of a unit vector is the vector over the magnitude of the vector. So we can take these and combine them to get our unit vector here. So this gives us u is our r vector was 2, 3, 6, over the magnitude, which is 7. This gives us, if we go ahead and divide straight across, 2/7 is our x component, 3/7 is our y component, and 6/7 is our z component. So this is the unit vector. In order to get the force vector, we will multiply by the magnitude of the force here. That's our 700 pounds times the unit vector. So that's 700 times 2/7, 3/7, and 6/7. This gives us our force vector of 200, 300, and 600 for the x, y, and z components, which you can write either in these brackets here, or if you prefer, you can use the IJK system, which is 200 I hat plus 300 J hat plus 600 K hat, and then of course at the end, pounds. Either one of these is a correct answer. You can write it either way. It's whatever your preference is. So this is how we would use unit vectors to convert to Cartesian form, and from this we could even go back to polar form if we wanted to, using our cosine alpha, cosine gamma, cosine beta to find each of the polar components.